Gosh. It's not looking good on Zoom. It's not looking good on Zoom at all. Okay, it's better. Let's see. Okay, can you put it in presentation mode though? That's what I need, and people in Zoom need. It's the same thing. Okay, much better now. Okay, I'll do that, yeah. Okay, let's get started. Why do you use multiple screens? Can you fix this? Let's. You can see that even a simple system like this is not dependable. So that's why dependable computing is perhaps the most important subject we have going into the future, frankly. How do we make computers more trustworthy and dependable? If we cannot make these trustworthy and dependable, how are we going to make something else dependable, right? Okay, this is wrong. This is the wrong slide set. You need to go to 2A. We're going to start soon, hopefully. You can take your break earlier. Okay. If I do this, will it? Okay, that's much better. Okay, so let's get started. Thank you. Yeah, we're going to continue where we left off yesterday. And today, hopefully, we're going to start with combinational logic and start with the transistor abstraction. How many people have seen transistors before? So you know what a transistor is. How many people do not know what a transistor is? Well, you may know the word transistor. Knowing a word doesn't mean that you know what it is, right? I know the word transistor, but I may not know what it is underneath. And you may know it at a different level of abstraction. We talked about Feynman yesterday. Feynman was great at criticizing, critiquing this, knowing something and knowing of something or about something, right? Knowing the word transistor doesn't mean that you know the transistor. So let me see a show of hands. How many people know how a transistor works? Okay, so how many people do not know how a transistor works? Okay, that's good also. So you'll hopefully learn something, hopefully in the second part of the lecture, because I still want to cover some things related to what we did yesterday, although we're going to hopefully go over this relatively quickly. So yesterday we did a lot of motivation. By the way, I hope people in Zoom are hearing us also. I can see the slides in Zoom, but I don't know why it's not moving. Yeah, apparently slides in Zoom are not moving, guys. If you're logged into Zoom, you're not seeing anything. And I see a lot of people logged into Zoom today, actually. And I don't know if the slides are moving on YouTube. Yeah, anyway, let me do something over here.
Now it's moving.
Okay, now it's moving. Are you sure?
Yeah.
Okay. Okay, hopefully they keep on moving. You don't want your car, self-driving car, not to be moving in a critical situation or moving in a critical situation, right? You want basically dependability. Okay, so yesterday we were talking about many interesting things that are happening in architecture. And remember, we talked about performance, energy efficiency, sustainability issues, people developing specialized accelerators, looking at new topics like processing in memory. This is all happening. And we talked about reliability, safety, security, and privacy, which we just saw an example of. This is an example of dependability. And then we talked about more demanding workloads and some new device technologies. This was an overview, of course, right? We didn't go into a lot of detail on any of these. But let's talk about more demanding workloads a little bit more. I hope these are the latest set of slides because I see a slide missing in between this and that, this and the next one, but hopefully it'll be okay. So as we discussed yesterday, computing today is very much bottlenecked by data. We can generate a lot of data. In many applications, data is really key. All important workloads are data intensive, and they require rapid and efficient processing of data. And we're trying to do increasingly more sophisticated things on the data, right? We're doing a lot of data mining. Machine learning models today, we rely on a lot of data, very heavy amounts of data to learn things, right? Or to statistically find correlations among things so that they can infer something and predict something maybe into the future or give a new input data. So it's good to, I think, consider what we mean by learning. This term learning is a bit abused today, in my opinion. Are these systems really learning truly? Are they really understanding what they learn? Like, what is the level of learning? Or are they really memorizing some correlations that they've seen in the past? So I think it's good to be very critical, especially in a scientific environment, and so that we don't really get caught in hypes that may make us think that, oh, we've solved the learning problem. I think we're very far away from solving the learning problem because computers don't really understand the decisions they make, in my opinion. They just find correlations between the data. Yes, they're much better than the past, but there's much more to do going into the future. But anyway, they rely on data, and data is really increasing. We can generate much more data than we can process. These are some traditional workloads that people have been working on, data centers, for example, data analytics. And these are all data bottlenecked, actually. There are a lot of studies that show, these are actually some references to studies that show that these are bottlenecked by data. And data really bottlenecks the performance and energy of computation. And then there's these workloads that we have studied actually very closely in our research together with Google. And these are some workloads that we're exercising today, actually. We are exercising the browsing. We're exercising the codecs on YouTube because we're live streaming these lectures. So these workloads are being exercised right now. And I bet we're exercising some TensorFlow structures, especially if people are watching this lecture on YouTube, for example, on their cell phones. So these workloads are being used right now as we deliver this lecture. Somebody's collecting data using the TensorFlow infrastructure, using machine learning, and maybe there are predictions that are happening while people are watching as well. So keep this in mind. These workloads are always run today. I'm not even going to touch that so that I don't destroy something in the infrastructure. And it turns out these workloads are also very much bottlenecked by data. So we did this study with Google some years ago. We analyzed these 4 workloads that I showed you over here, and we found out that more than 60% of the total system energy in these workloads in a mobile system, like a cell phone, Android phone in this particular case, is spent on moving data between the processor and memory units, main memory. We didn't even look at storage because we assumed that the workloads are in the main memory, actually. So this is a large amount. Actually, 60% is an underestimate because we did another study with Google, again, together with their models that they use in their edge devices. These are neural network models, cutting-edge neural network models run on cutting-edge neural network accelerators that are built into mobile devices. And we found out that more than 90% of the total system energy is spent inside the memory, just moving data back and forth between the processor and memory, and also in the memory system to do inference in the large machine learning models that we study. This is a lot. In some cases, it's 99%. So imagine this, right? We're designing these computing systems, and most of the energy is spent on moving data around. So this is important. Don't lose the forest. This is the forest, basically. The energy, the big thing is really data and memory. We're going to talk a lot about computation. That's really important. But today, we're not bottlenecked by computation in many cases. We're bottlenecked by memory. So we'll see memory toward the end of this course. That's the importance of what we're going to build up to toward the end of this course. Okay, and the reason is, you've already seen this before, the reason is data movement is expensive. And we're going to talk about why it's expensive, but the key thing is it goes through large interconnects. And as the large interconnects become more power hungry, and if they become longer, they become less and less efficient. So energy is really spent on interconnects. Whereas the computation units, like we will see today, hopefully in combinational logic, is very much efficient today. And we'll see this picture later on also. And you've already seen this also, right? Even simple computations are even more energy efficient. As a result, comparatively, a memory accessing data from memory is much more expensive. And if you look at the storage system, if you're accessing an SSD, that number can go up to 1,000,000x. So an SSD access can be about 6 orders of magnitude more energy costly than a single arithmetic computation like an addition. So keep that in mind. Does it really make sense to actually access the SSDs a lot? It doesn't. We'll see some ideas like that, some ideas to minimize the accesses to memory and storage, but it doesn't always work. Okay, so we're going to hopefully finish with these interesting things and then start with the material. But basically, this is a summary of what we've covered. Basically, today, we're investigating many novel concepts, new computing paradigms, processing in memory, processing near data. We discussed it. There's neuromorphic computing and quantum computing we did not discuss because I think they're a bit farther away, quantum computing being even more farther away than what people may people may think. May want you to think. I believe there's still a lot of revolutions that need to happen in quantum computing for that to actually be a general purpose paradigm. It can be a specialized accelerator, but general purpose paradigm is very difficult, I think, at least within the short term. Fundamentally secure and dependable computers, that's something we should think about as we discussed. We talked about new accelerators and systems. These are usually algorithm hardware co-designs. They're not just an accelerator put in hardware. You need to design the algorithm to take advantage of it as well, and the system software stack. So we talked about things for artificial intelligence and machine learning, graph and data analytics, vision, video. Actually, video acceleration already exists, as we discussed, and vision acceleration already exists also, GPUs, and graphics acceleration also already exists. Genome analysis is coming in the future, and it's already happening in some places, like sequencing companies that design sequencing devices because they know the problem and they can integrate these accelerators in their sequencing devices. And then we talked briefly about new memory, storage systems, interconnects, and devices. So there's a lot happening in this as well, but we'll see some of these later on in this course. And we talked about applications. Applications will continue to be more demanding. If anybody says that applications will not, there will not be better applications, better from some perspective of better, of course, right? Don't believe them because people are very imaginative and creative, and they're going to solve a lot of problems with new applications. And they're increasingly diverging and complex trade-offs like the memory processor bottleneck dichotomy. And the systems are a lot more complex as a result. Basically, past systems looked simple like this: processor, memory, storage. But today's systems, even this doesn't really do justice to their complexity, but they're much more heterogeneous, basically. It's not just general purpose CPUs, but you have heterogeneous SoC system on chips. There are FPGAs, which we will talk about. There's hybrid main memory. There's general purpose GPUs. There's persistent memory and storage. And then there are high-speed interconnects that you can connect to. So it's actually much more complicated than in the past. And this picture does more justice to the SoC part of it, basically. And even this is old, right? You can see that a GPU is integrated onto the chip, onto the system on a chip. And there are neural engines also. These are essentially machine learning accelerators that are over here. And then different types of cores as well, right? Some of those are high performance cores. Some of them are more energy efficient cores. Okay, these are nice pictures to look at. So I think the takeaway is everything is being re-examined. And we've seen this slide also last time today. So you're at a good point, actually, to be looking at these things. Like when I started my bachelor's degree, when I was sitting similarly in 1998, it was a bit more different. Basically, these heterogeneous GPUs were just being examined by people as devices that they can use to accelerate applications. They were not mainstream at all. Today, GPU is a mainstream, right? It's everywhere. So you're in a different point in time than when I started. So at this different point in time, a lot of things are changing much faster, actually. And you can actually revolutionize the way computers are built if you know what's going on underneath as well as at the higher levels. Basically, think about both hardware and software. So it's good not to compartmentalize yourself as a hardware person or a software person. I think of myself as a systems person, let's say. I can work on hardware and as well as the software because it's really important to design systems as we discussed, right? So if you understand both very well, and if you can design each accordingly to design a much better system, you're much better off. And you can also invent new paradigms for computation, communication, and storage. And we'll see some of these paradigms. How many people know this book? Okay, how many people do not know it? I guess it's always asked a complimentary question. That's good. So this is a book that's very famous, actually, in history of science. This person, Thomas Kuhn, gives a lot of examples in this book on how scientific revolutions happen, how paradigms change basically, in systems. And this is actually, he gives a lot of examples from physics and chemistry and astronomy, for example. So sometimes there's in science, there are a lot of debates about different things, but let me actually put the whole thing over here. There's some normal science, and normal science is the mode where there's the dominant theory, and that is assumed to explain everything. For example, this processor is able to execute all applications. This was in 1990s a CPU, a high-performance CPU like we will build in this course. But then, over time, applications evolve, demands of people evolve, etc., and people figure out that this processor is not good at executing many workloads. And people start questioning, basically. And then there becomes pre-paradigm science, or people start examining the underlying assumptions. And then no clear consensus in the field comes. Basically, people say, oh, okay, we should really build machine learning accelerators, or we should build GPUs, or we should build FPGAs. So we should build this heterogeneous mix of things so that we can take advantage of many different, we can execute many applications much faster and at higher efficiency. So I'm kind of applying these principles of normal science to evolutionary science, of pre-paradigm science, to computer engineering, if you will, or computer science or computer architecture. And this is what's happening in computer architecture today. There's no consensus today on what is the best way of building a computer. Basically, the answer is it depends. There's no dominant way also, basically. There's no one who can claim today that this is the best way to build a computer for applications. It really depends on the application. It depends on the use case. And it depends on the user also, who's going to use it and their requirements. That's why we're seeing this huge proliferation of different types of architectures and different types of paradigms. And a lot of them are being integrated into the same system. So this has actually multiple different paradigms integrated into it. It used to be very different computers that are designed for different purposes. But one of them was dominant in 1990s, which is a high-performance pipelined out-of-order execution superscalar processor, as we will build. If you didn't understand the out-of-order execution superscaler with branch prediction, you will see all of those later in this course. But that's not the only thing inside here today. So basically, we're still in the pre-paradigm science over here. I think pre-paradigm and evolutionary overlaps as well, as Thomas Kuhn discusses. So if you're interested, this is the guy or the author. And this is his paper. Or not paper, sorry, books. And I would strongly recommend it, actually. It's a beautiful book. It gives you a lot of insight into also how science evolves. Because if you look at the discussions in science, it's not like if somebody proves something, everybody accepts it. It doesn't work that way. It's actually, there's a lot of resistance to results. For example, if somebody shows that a theory is wrong based on one experiment, there's clear resistance from the people who actually developed that theory in the past. So there are human factors that go into it also. So how does science work to convince people that one theory is better than the other over time? So it's a process that happens over time. It doesn't just happen with a single experiment. Single experiment may have importance, but there are human factors involved, and those human factors move much less quickly than the experimentation, if you will. So these are actual lessons for convincing people also, right? If you go into, I don't know, politics, which is almost extreme opposite of science, if you will, today, unfortunately, because most of the politicians ignore science. In fact, they're against science, which is really bad in general. So those are regressive politicians in general. But basically, if you go into politics, you can still take advantage of this book because you can see that how you can convince people, right? Assuming they're rational. Rationality is a very, I think rationality in human behavior has been very, let's say, overestimated assumption, especially with what we're seeing with social media today, right? Okay, so takeaways, I think, going back. It's an exciting time to be understanding and designing computing architectures today. There are many challenging and exciting problems that no one has tackled or even thought about before that can have huge impact on the world's future. We talk about sustainability, right? And this is really driven by many things, driven by the two major things, I would say, driven by the top as well as the bottom. At the top, we have an explosion of data, we have new applications, and even greater realism that's demanded by users, let's say. And we can easily collect more data than we can analyze and understand today. And that's really putting a lot of strain to our computing systems. At the bottom, remember, the top is problems, and the bottom is electrons, physics. There are significant difficulties in what we can do with physics today. because we are having trouble, like things like RowHammer we discussed, those are physical issues, right? But we're having a lot of issues with energy, reliability, complexity, security, scalability. And we will see some of these in these lectures. So I think two other major goals of this course for me is to enable you to think critically. I think it's really important to, at a place like ETH, you have to be critical thinkers because you're supposed to be, let's say, educated people who are going to determine the future of Switzerland and more broadly, the world, right? You have to think critically. If you're not going to think critically, who would? Always ask that question. And you should also be able to think broadly because there are many, many concerns that, that you need to think about when you design a computing system specifically, and when you design anything actually, and you need to be able to think broadly so that you can actually make the right decisions. Any questions? This is still high level. I'm going to stay a little bit more high level because I love these puzzles. I was going to update these slides with the puzzles, but I couldn't find the pictures on my phone. So you can see how bad the data is today, right? How do I find the pictures I want? I cannot say to my phone, maybe I can, but I don't want to do that. Something, and it gives me pictures, but I don't know. Okay, so let's start with some puzzles. I think, as I said, I love architecture and art, and I think computer architecture quite resembles building architecture. Of course, you should keep the analogy to reasonable levels, if you will. So I'll ask you the question, what is this? Has anyone seen this thing, this place? You've been there, people are, yes, please. That's right, yes. It's one of the train stations, but if you just say a train station in Zurich, it's not specific enough. Which one? Okay, early today. Yes, absolutely. This is Stadelhofen. And I think there may be, okay, this doesn't give any information about that. That's good. But you could, of course, take that and click on it and figure it out, but you didn't do that, I know. So yes, this is Bahnhof Stadelhofen. This is the same place from the top, basically. And the top is more famous than the bottom. So what do the following have common? What does Bahnhof Stadelhofen have in common with this one? This is, well, this you know what this is, Gare do Oriente in Lisbon. How many people know this place? Okay, you've been there? Me too, okay. And there's another one in Milwaukee, in the US, in Athens, in Greece. Beautiful. I've been there here also. These are beautiful structures, right? Ooh. I think universities would do better if they don't spend money on these structures and say spend money on real science, but fine. That's my commentary here. Certainly you don't need this one. But I mean, maybe you could make an argument saying that these are the people who should be advancing in architecture, right? At what cost? I don't know. And this is the Oculus. So any thoughts on what do these have in common with Stadelhofen? Anybody? There are some similarities, no? Yes. The arcs, exactly, yeah. I mean, if you look at this, there's some archy structure, and if you go back to Stadelhofen, this is not a great picture, but you can see those right over there. Yeah, and a lot of these actually have those type of structure. And this kind of resembles a bird, wings, yeah. And here it's flying. Here it's supposed to be also kind of flying, but it didn't because it was too expensive to make that happen. Okay, that's one thing. Basically, kind of the philosophy, design philosophy and principles actually are kind of similar. You had something else? Exactly. Do you know who that architect is? Calatrava. Yes, exactly. So that was another question, but there are multiple things and they're related basically. It's because they're all from the same architect who has some principled design, who happens to be also an ETH alumnus in civil engineering. They're very similar in some sense, although they've evolved, right? This is, actually, Stadelhofen was his first major project in 1980, 83 or something. And then he moved on to many other major projects. So you can see the train station has several of the features that became signatures of his work. Straight lines and right angles are rare. That's what you meant by arcs, I think, right? And that's him. You can read more about him. So this is your first assignment. I'm not going to grade you for it. Go and find the closest Calatrava building to this classroom. And it's not Stadelhofen. It happens. So you get 0 for that for Stadelhofen if you say that. Does anybody know what's the closest Calatrava building? Okay, there. Yes. Okay, that's a good one. I think people should verify that. I'll leave that to you. But yes, it's close by here, basically. It's very close by here. Very good. Okay. And yeah, there's another challenge, of course. You can try to find the furthest building that was designed by Kalastrava to this classroom. That may be a bit harder, but you can still do it right. I mean, this is precise. You can actually come up with an algorithm to solve this problem, right? This is a precise problem that I have defined over here. Closest versus farthest. Okay, and then you can appreciate the beauty and out of the box and creative thinking, which I always appreciate, actually. I sometimes go through Stahlhofen and I still have the same feeling over there, basically. I don't think of this as just a train station. I think of this as I wouldn't call it a masterpiece, but as the first major work of a principled architect who tried to design something that's better than before, let's say. And you can think of the trade-offs in the design, strengths, weaknesses, what are the goals of the design. And this could actually help you derive your own principles for good design and innovation. Of course, if you do it in a good way, right? So this is your due date. Feel free to send me an email. And I've gotten a lot of emails of Oculus. People like Oculus for some reason when they go there in New York City. We're going to talk about that a little bit more. And people have taken pictures who've taken this course or my past courses. They've taken pictures with Oculus and said that, oh, that's a great place. Thank you. Okay, and you can apply what you learned in this course and think out of the box. But today's first assignment is something simple. I'm going to show you multiple pictures. This picture, this is Stahlhofen, and this picture. What is this? Where is this? Don't look here. Okay, sorry. I already put it actually because somebody actually mentioned it, so you know where it is now. Okay, so maybe I'll answer the question. Basically, there's a difference, right? This is a more run-of-the-mill regular train station. It's fine, but it's designed for different goals, right? Think of it that way. There's clearly a difference in terms of cost also. This is certainly more costly actually because of the construction materials used and the structures that are designed. It's not as simple as this one. So again, there are many trade-offs between the design. My point is that these two designs, you cannot call one better than the other. It really depends on what is the goal, what are the metrics you're evaluating with. If your metric is artistic creativity, probably the first one is better than the other, right? Because it's more unique, let's say, right? It's very hard to call something creative if it's the same thing stamped out a million times in the past. That's not artistic creativity, right? It's more like replicating what was done before. So if that's your metric, then the first one wins. But if your metric is cost, the second one wins, right? Because I would take this one if my goal is only cost. If my goal is a trade-off between the two, I want both artistic creativity and also optimize the cost, then it becomes a little bit less clear, right? Which one is really better. But there are many, many other metrics, right? Functionality, certainly does it meet the specification? Reliability, is it going to collapse on you soon or in the event of some disaster, right? Space requirements, cost, expandability, comfort level of the users, happiness of the users. These are two different things. Again, you could actually add more, X of the users, Y of the users, Z of the users. Aesthetics, which is similar to artistic creativity, but not necessarily. Security, and a bunch of other metrics, basically. And these metrics are actually applicable to architecture, and a lot of these are actually applicable to computing architectures as well, right? Comfort, happiness. I may be very happy with my cell phone, right? That's a computing system. But if something changes, I may not be very happy the next moment, right? If someone takes it over, for example. So there are actually relationships between the metrics also. So it's good to think about this. And when we actually talk about computing architectures going forward, I want you to think about this metric-based thinking, because that's what enables trade-offs in the design, and that's what enables us to evaluate different designs comparatively to each other. So that's basically what is called performance evaluation. Performance in general, performance could be evaluated with many different metrics, and how to evaluate goodness of design is always a critical question. So I'll keep this at this level right now. We're going to see some performance metrics later on. Actually, today, hopefully, we'll get to energy evaluation a little bit when we talk about logic gates. We'll see how far we get along today, but yeah. So a key question is, let's switch gears a little bit. How was Kalatrava able to design especially ski buildings? You can have many guesses over here, right? This is my long list. Again, I have ... but hard work, perseverance, dedication over decades. I mean, these are actually also some characteristics of, let's say, strong architects And I'm using the word architect very generally right now. I'm not saying computing architect or building architect. I believe there's actually characteristics of all architects who really want to do something new and change the world, if you will. So experience, creativity, out-of-the-box thinking, a good understanding of past designs. That's why you need to study the past. Good judgment and intuition. That's really important to develop, actually. And a strong skill combination. He was actually educated in multiple things. He was a civil engineer, but he did a lot of architecture, and he actually studied math as well. And then initiative to make things happen, entrepreneurialism, funding, or figuring out where the funding comes from, and some luck also helps. But usually you can potentially shape your luck if you actually prepare really well. It was Louis Pasteur who said actually, chance favors the prepared mind. And I strongly believe that actually. If you're prepared to see something, you can see something. But if you're not prepared, if you don't have the background to see an opportunity, that opportunity comes to you, and even if it comes right in front of your eyes, you'll just miss it. So preparation is extremely important to bias your luck to yourself. And then strong understanding and commitment to fundamentals and principle design. I will especially talk about the second two soon. But hopefully you'll be exposed to a lot of these in this course also. That's what I mean by critical and broad thinking over here. So let's see. So principle design and strong understanding of fundamentals. So let's talk about principle design, because fundamentals we're going to cover. So you need to know the fundamentals to build something like that, right? If your fundamentals are not good, whatever you build will not be good in the end. So these are the principles from his own words, basically. To me, there are two overriding principles to be found in nature, which are most appropriate for building. One is the optimal use of material. The other, the capacity of organisms to change shape, to grow, and to move. So now you can see where the arcs are kind of coming from. It's the second part. Optimal use of material is potentially more debatable, especially given the cost of his structures. But still, that's his principles. That's what he thinks he's applying to his buildings. And these are from some other people, right? Calatrava's constructions are inspired by natural forms like plants, bird wings, and the human body. This is actually some anthropomorphic thing. Can people see that? Like, I don't know if I can point these. Look at these things. Look at the face, arms, body, kind of legs. They look like bats. And that's his blueprint. So this is actually a principle design that he pioneered, which is zoomorphic architecture. Architecture is based on zoomorphic shapes, animal forms, essentially. Okay, you can read more about this. This is not the subject, but you will see actually in computing architectures, you have different principle designs also, right? Some principles will basically say, we're going to design the computer architecture so that the hardware is going to be as simple as possible, and compiler is going to extract the parallelism in programs. That's a principle, and we will see that in the VLIW systems. And then there's another principle design that says, we're not going to trust the compiler or the programmer. We're going to design the hardware to be complex and to extract the parallelism automatically to make the life easier for the programmer, so that the programmer doesn't do anything, compiler doesn't do anything. This is a very more hardware-centric way of extracting parallelism, and that's another principled approach. So out-of-order execution has been developed based on that principled approach. And actually there was good reason for that principle, because we're not going to trust the compiler was a reasonable approach, because compiler technology was not very well developed in the 1960s, 70s, 80s, until actually 1990s, in fact. Right now, compiler technology is very well developed, but we will see trade-offs between compiler and hardware. What can the compiler do? What cannot the compiler do so easily? And what can the hardware do easily versus what cannot the hardware do so easily? So that's why I'm talking about these things, basically. These things are actually, in my opinion, very directly analogous to what we have in architectures. And we will see more of these. Okay, you can see more. So what does this remind you of? Yes? A bird. Okay, good. What kind of bird, I will not ask. Some kind of bird. But yes, it's a bit, Calatrava's imagination is a little bit different, as you can see, but it's still a bird, right? It resembles a bird being released from a child's hand. And you can see that the roof was originally designed to mechanically open to increase light and ventilation. But folks in New York City said, we're not going to pay you more. So cost is always a concern. So you can see that people are actually analyzing it with their trade-offs. In fact, this journalist says, it's a pleasure to report for once that public officials are not overstating the case when they describe a design as breathtaking. They have a healthy criticism of public officials also inside here, as you can see. So So they're design constraints. So design constraints are actually very important in any architecture, including building architectures. As you can see, security is very important. In the name of security, Santiago Calatrava's bird has grown a beak. The ribs have doubled in number and its wings have lost their interstices of glass. The main transit hall between blah, blah, will almost certainly lose some of its delicate quality while gaining structural expressiveness. It may now evoke a slender stegosaurus more than it does a bird. And if you don't know what that is, that's this. Which actually you can imagine is similar to that also. So you can see similarities. So you can see that basically you're never immune to design constraints, and no one is immune. If someone says, I don't care about security, that's the weakest point basically of the design. So you need to be very careful when you're designing. In fact, cost, if no one's immune, cost is a concern all the time. Sometimes when I talk to people who build supercomputers or who build things for the government, for example, they claim cost is not a concern for us. I say, okay, let's talk 2 years later. We talk 2 years later and they say, oh, you cannot do this because that's costly. Well, you didn't say, you said that cost is not a concern for you. What happened? Well, you don't have deep enough pockets, and nobody has deep enough pockets for this. Nobody should have also, perhaps, but basically you can see that cost also came to, they had to eliminate the opening and closing of the roof because of budget and space constraints. And you can see the cost also, it's almost $4 billion according to this article, which is on Wikipedia. Okay, so let me give you the very quick overview of how different this lecture was when I was at CMU. Does anybody know this place? Yes? Where? What is it, I guess? Maybe I'll pick on you. Okay, who? Our architecture class. Art class, okay, interesting. So you can see how influential architects are. Yes, anybody? Anybody wants to guess? Yes. Falling Water, okay, have you been there? No? Have you been there? Okay, I would recommend you go there because it's an amazing place. The pictures don't do justice to it. This is the architect, another hard-headed architect, I would say, Frank Lloyd Wright. And I mean, this is, as you can see, in Smithsonian's probably biased life list, it's one of the 28 places to visit before you die. I should probably say probably biased because 28 is a small number. Okay, let's find the difference of this and that, but it's still great. I mean, this is not a criticism of the work. This is a criticism of that selection process, if you will. And any selection process like that is probably biased. Okay, let's take a look at this difference between this. This is another view, actually. This is, I believe I took this picture, but I'm not sure. I took a lot of pictures. So this is Falling Water, and this is that. So you can make a similar analysis over here. Again, which one's better? It depends. It's a trade-off analysis, right? It depends on what's the metric, right? If it's cost, definitely I will take this one. And if it's cost, and if it's a trade-off between cost and also living in nature, maybe I'll take this one, right? Because I cannot afford this probably. And also this was not very dependable when it was built. The latter one may be more dependable because here, he really wanted to optimize things so that if you look at this, there's a waterfall and the building is imitating the waterfalls. There's these cantilevers over here. This is the top waterfall and this is the bottom waterfall over here. And it was actually not an easy thing to design. It's an old structure also. Okay, yeah, it's the same thing. How was Frank Lloyd Wright able to design this masterpiece? Well, you can list things. And principle design is another one. This is a quote from the architect himself. I really like this. Basically, he says architecture should be based upon principle and not upon precedent. Precedent is what comes before, right? Basically, you should really build architectures based on principle and not what comes before, because what comes before may not be good in many senses of the good. But I would like you to think about this a little bit. You should really understand what comes before so that you can improve your principles, but this doesn't mean that keep doing the same thing as in the past, because if you do that, there's no progress into the future. And our goal at a university especially is progress, right? Progress in education, progress in research, progress in science. In my opinion, there's not much other goal. Progress in education is getting educated to do progress. Okay, so basically this is precedent and this is his principled design. Again, you could argue, you could basically evaluate these based on different metrics. This doesn't mean that this is necessarily better, but it's better in some metrics for sure. And this is the principle basically used. It's the philosophy of architecture, which promotes harmony between human habitation and nature, again. And you can see over here more. Okay. And I already gave you an example of the synergy between the falling water underneath, that's flowing underneath the building, and the building that's built on top of the multiple waterfalls, right? Those are the cantilevers. Yeah, this picture doesn't do justice to it, but this picture clearly shows that there is some synergy or similarity between these and these over here. Okay. Okay, so I think takeaways, in my opinion, are these basically. It all starts from the basic building blocks and design principles, and you need to know them really well before you do something big, and the knowledge of how to use, apply, and enhance them. In fact, underlying technology might change, and people have seen this in architecture. It could be steel versus wood in building architecture, but methods of taking advantage of technology bear some resemblance. So some principles remain similar, but sometimes some principles get enhanced by the technology as well. So methods used for design depend on the principles employed. So basically, the reason I'm telling you all this is, again, this applies to processor chips also. So there are some basic building blocks and design principles over here. These are multi-core processors, and they have similar design principles in that they put multiple different processors and they replicate them in the hopes that they will get more parallelism, and the software will exploit that parallelism. Some of them are a little bit, they also differ in their principles sometimes, because some of them put very sophisticated cores, like IBM Power 7, for example, puts very heavy cores, whereas this Tile GX puts very, very simple cores. So the expectation from the software is very different between these two. In Power 7, for example, the software doesn't need to be that complicated. Here, the software needs to be very complicated to take advantage of 100 cores or so, very parallel, etc. So they actually employ different principles to design these chips. And we're going to see all of those, well, all of those, an overstatement, many of those principles. And that's why I showed you these pictures, which I'm going to just push through right now. So these all, basically keep in mind that these are not just pictures, these are actually principled designs. Some parts may be hacky designs also. We will talk about that maybe. Actually, we will talk about that later, not today. Okay, so processing and memory systems are also being designed today. Okay, I've already said this. So what are the basic building blocks that we will come up with, we will study in this lecture? Well, we will study the electrons. I'm not going to tell you about electrons, but we're going to talk about transistors very soon. And then we're going to build logic gates, again, very soon, meaning today, at the second part of this lecture. And then we're going to build combinational logic circuits. We're going to start that again today. And then next week, we're going to start with sequential logic circuits. Combinational logic circuits are logic circuits that don't have memory. Sequential logic circuits have memory. They can remember the past, basically, which is a really critical thing to do, clearly, when you need to do computation, remembering the past, right? Remembering what happened before. And then we're going to build more and more sophisticated building blocks like cores, caches, interconnect, and memories. Does that sound good? Yeah. And then you can actually build different types of chips and then put them together in a system, right? These are basically building blocks progressively we're going to build up. Okay, so you have some reading assignments for this week and next week. These are the two major books we're going to use, especially in, let's say, first half of this course. There's a second half of this course. We will use some of these also, but I'll supplement it with other readings because, unfortunately, a textbook for this course, full textbook for this course doesn't exist. I need to write it, I think, but I don't have time to write it. So I will try to write it sometime. Until I write it, unfortunately, we're going to read other books. That doesn't mean that these are bad books, by the way. These are actually very, very good books. I like them. I actually studied this book. Pat and Patel, Yale Pat was my advisor at the University of Michigan. And then I took my first class from Yale Pat, and then I became his PhD student later on also. At that time in 1998, this was not a book. This was just a number of sheets of paper that we studied from. Now it's a book, and there's a third edition actually of this. And it's beautiful, I think. So for Harris and Harris, we're going to actually cover a lot of this. It takes a very different approach than the first one over here. And there's some parts in the Harris and Harris book that doesn't exist here, and vice versa. Basically, that's why we use two books. And these are not the latest editions, but I believe latest editions are not that different also. So if you take the latest edition of the first book, which I believe is in the library, I think one of you mentioned it via email, you're not going to get something different. The only difference will be the latest edition, I believe, is in RISC-V, which is a different ISA than what we will cover in this course, which is MIPS. But again, you will see that the ISIs are also ISAs are also very similar, regardless of however they're marketed. I believe actually RISC-V is very, very similar to MIPS in terms of its design, and you may see that also. But there are some differences in different editions, and maybe what I refer to in the lectures do not exactly match in terms of the sections. So you'll have to do some remapping, if you will. But we'll try to do that. If you do that remapping, please let me know so that we can fix the slides for different editions. We're not going to cover binary numbers. How many people covered binary numbers? Okay, how many people did not cover binary numbers? Okay, that's what I expected. When did you cover binary numbers? If you covered it, high school? Yes, high school. Who says high school? Okay, who says not high school, university? If you covered it, okay, that's good. Okay, so we made this decision that we're not going to recover high school material, which I think is kind of boring, right? It's good to know binary numbers, of course. So you'll need to learn binary numbers if you haven't learned about it. It's very easy. You're not going to have trouble with this one, in my opinion. So supplementary lecture slides on binary numbers are available. And these books also don't cover it, by the way, they assume it. Okay, so I've already discussed the high-level goals of this course, so I'm not going to cover this again. And as I said, the goal is to understand how computers work, and because main reason is you're here for a computer science degree, and it'd be kind of a shame if we don't give you the opportunity to understand how a computer works if you're going to claim that you're going to be a computer scientist, right? But regardless of that, I think hopefully what we cover will be useful for you, regardless of your future direction. Let me very quickly cover course info and logistics, and then we're going to take a break, and then we're going to start with the next section. We already covered this. I think we didn't cover this, but Mohammed is one of the head assistants over there. Mohammed, you can show yourself. Juan is another one. He's traveling to Montreal right now because we're going to give a tutorial in Montreal, which I'm not looking forward to because it's like -16 degrees in Montreal at night. But yeah, he's another head assistant. We had a head lab assistant, Ataberk, who was here yesterday, but who's not here today. And we have a, let's say, lecturer, Frank, but he will cover lectures when I'm not around or when Mohammed cannot do it also. And then we have also Mohammed Alser, who's not here. I think a lot of people are not here, but I'll mention the two TAs over here, key assistants, Nika, and then Rakesh over here. And then we have a bunch more. These are all my PhD students or like interns, people I work with. They all do research also, so you can get to know them and their research. And then we have a bunch of student assistants who have, almost all of them have previously taken this course actually and did well. And they wanted to basically help with the course, and you can see a bunch of them over here. I would suggest interacting with them and going to the assistant that you think you connect with the most, because there's a lot of opportunity for that in this course. And you need to figure that out, of course. I cannot figure that out for you, sorry. I can do a static assignment, of course, but that's not going to scale very well or work well. Okay, and then there are labs, and these are going to be assigned. We don't know that yet. Labs will start soon, as I will show you soon. If you need help, you can, of course, post to Moodle for technical questions. If you have a personal question, you should send it to me and this list, and that list goes to all of the assistants, does that go to student assistants also? Okay, everyone basically. But if you really have a personal question that I need to deal with, you should send it to me and the head TAs, who are Juan and Mohammed. Yeah, there will be office hours, and we will provide these will be hybrid. I think it's hard for me to imagine that after some number of years of pandemic, people are not having hybrid things in the world. But this will be hybrid, basically. I think we should have learned our lesson, but humanity takes many, many years to learn their lessons, I think. Yeah, we'll provide the office locations if you choose to do that, or we'll provide the Zoom links if you choose to join via Zoom. And these will be posted via Moodle and your email. And then we already discussed the course website. You can find a lot of information over there, including links to previous exams, etc. And your ETH email and lectures and teaching assistants are available to you to ask questions. As I said, if you send email to me, please also CC some of the assistants, especially the lead assistants, if that's an important thing that we should look at, because I get a lot of email, and my email and myself are not very dependable, let's say. I'm not a dependable computer. I miss a lot of email. For example, I'm going to travel tomorrow to Montreal, and I'm going to miss a lot of email. And the backlog is going to be long, let's say. And I can guarantee you that I'm not going to be able to recover that backlog. So fault tolerance helps. If you send multiple emails, the likelihood of me seeing that email increases. Now you can see a dynamic system, right? Okay, so I think this is kind of obvious, so I'm not going to spend a lot of time over here, but we already discussed lectures and then lab sessions. You should definitely attend the lab sessions, I would say. There's an in-class evaluation, and there's mandatory lab reports. And labs will start March 7th, and there's lab information over here, and we will actually give you more information. By the way, another TA came over here. He's Joel. He's also a PhD student with me, and he took this course. When did you take this course? 2017. I think that was the first time I was lecturing that. Yeah, that was a different course at the time. He took a different version. It evolved, basically. Okay, so you will have lab groups. So you can actually study this material. You need to choose your preferred group in Moodle, choose your partner, choose on-site or online. Yeah, and these are due March 3rd, as you can see over here. These are all Moodle links, and you have all these slides online already. You may be able to use lab grades from previous years if you're retaking this course, and you'll need to choose one of these options, as you can see, again, on Moodle at the same time as the stuff that's on the slide. Okay, final exam. I think we covered this yesterday. Yeah, I don't want to spend more time on this than yesterday. If this is your only focus in this course, I'm fine with that. That's your problem. That's your choice. But if this is your only focusing course, then know that that's your only focusing course and take actions to make sure that your only focus doesn't get derailed. Hopefully that makes sense, right? Okay, so there's some, as I said, we're going to put a lot more information. Okay, reading assignments, I already said this. And next week, actually, we'll have a lot more reading assignments. So a little bit more on reading assignments. We actually will have more readings for the beginning of the course. So this may look very heavy, but at the beginning of the course, we'll have a lot more readings because a lot more readings are available. Yeah, that's how it is basically. But in the second half of the course, you'll have a lot fewer readings, and it's going to be more lecture dependent. And lectures have synergy with the readings. I cover a lot of material from the readings, but I also enhance them with different stories that don't exist in the readings. Okay, actually, there are some required readings that we say required. Required means these are actually related to the material that we cover in the lecture. Recommended means we recommend it, but they may or may not be related. And then mentioned means they're just mentioned, right? It's just for your benefit, right? So required are the ones to focus on if you want to read something that's actually related to the lectures closely. Okay, as I said, you can be a last time predictor. You can predict what's going to happen in the next lectures based on the past schedules. Although you'll be a little bit disappointed because if you made the prediction based on last year's lecture, this lecture is not going to be the same as last year's lecture. We'll start combinational logic today as opposed to lecture, I believe, 4, which was lecture 4 last year. Okay, any questions? If there are no questions, let's take a break. And again, let's come back at 3:20. So we seem to be very consistent in exact timing. And then we'll start combinational logic. Nah, what is this? Okay, yeah, please. Okay, let's get started with the second part of today's lecture. So as I said, if you looked at spring 2022 lectures, this is going to be when your predictor is going to be wrong, because we're going to cover something further in spring 2022 lectures. This is lecture 4 in spring 2022, but we pulled it back and got rid of some other material, which is also quite interesting, but you can always watch it from spring 22 if you want. So a wrong prediction, I guess in this case, okay, because you're not hurt or anything, right? That's fine. We will see prediction mechanisms and they being wrong in existing processors in lecture 16, 17, 18. Okay, this is also where your first extra credit assignment comes. There's no, you don't have to do this, but if you want to get 1% extra credit in this course, I would recommend doing it. Basically, it's a talk that I delivered in October about processing in memory, or how to build intelligent architectures for intelligent machines of the future. It's only 33 minutes, and you can write a review of it just for 1% extra. Well, I shouldn't say just, because 1% extra credit for this effort is pretty large, I would say. It affects your grade immediately with 1%, right? But I would like a good one-page summary following some guidelines, which we're going to provide online also. Basically, what are your key takeaways? What did you learn? What did you like or dislike? And I put the deadline as April 1st for now. Does that sound good? Yeah. If you want to get almost a freebie 1%, this is your freebie moment. I mean, you need to put some effort, of course, right? You cannot just put garbage in that, because if in the past people have put garbage and they got 0 points. So if you put garbage, that's what it will be. And don't put duplicates with your friends, if you will, because you'll also get 0 points. Yeah. Okay. Okay, these are more reading assignments, basically combination. This is for combinational logic. So combinational logic is covered, but somebody asked the question, if we have time or resources or money or whatever to focus on only one book, which one should we focus on? My recommendation would be to focus on the Harris and Harris book, because we're going to cover more readings from Harris and Harris and fewer readings from Pat and Patel. They're both good books, but that's how it is, basically. Unfortunately, there's no best book, right? Books are also trade-offs. It depends on what metric you're going to optimize for. And our goal is to give you the best material as opposed to follow one book. Following one book doesn't correspond with the goal of giving you the best material, basically, because that book has its own downsides, and we want to avoid those downsides, right? That's the reason why there's no single book. Okay, but combination logic is covered in Pat and Patel here, and Harris and Harris chapter 2. But you should also read chapter 1 of Harris and Harris, because it actually has material that leads to combinational logic, which we will talk about today. And then next week, we're going to cover sequential logic and hardware description language and Verilog, and this will be useful for your labs as well. Basically, within 2 to 3 weeks, we will be done with a lot of chapters. This may sound intimidating, but as I said, this course is a bit heavy in terms of readings at the beginning of the course. And if you really understand everything in the lectures, I do not believe you have to do the readings. But of course, readings are always a little bit more detailed in some aspects and a little bit less detailed in some aspects. So you will get something else from the readings. Okay, before I move on to computational logic, I should also emphasize what I said earlier. This may seem like this is only computer hardware, but it's really about hardware and the software and the interface between them. And also, you'll be much more capable if you master both hardware and the software and the interface between them. And it's already happening. People who really drive innovation understand both. And you can develop better software if you understand the hardware, and you can design better hardware if you understand the software. And you can design a better computing system if you actually understand both. And I've already shown you examples of that. So we cover the software interface and microarchitecture. And as I said, we'll focus on trade-offs and how they affect software as well as hardware. And examples were the chips and the platforms we kind of surveyed in the last 1.5 lectures. But now let's start understanding the fundamentals, because you can only change the world if you understand it well enough, right? Especially the basics. So we'll cover past and present dominant paradigms and their advantages and shortcomings. Okay, we're going to talk about these. So let's start with this. So what is a computer, basically? A computer is clearly this, and this, And this is also a computer. And there's a computer here hiding, right? And there are computers that we don't see, right? But any computer that's built today has three components: computation, communication, storage, and memory. And this is von Neumann, who actually we will talk about. He is the, let's say, the inventor, the co-inventor of the von Neumann processing paradigm that we will cover in lecture 9 or so. But wait for that. That's the paper that introduces it. And if you look at a computing system, it looks like this. Today, they're kind of decoupled, as we discussed earlier. But there are elements of memory inside the computing unit, and there are elements of communication inside the computing unit also. This you can think of as a computing chip. And then there are some interconnects, and then memory chips, and then storage chips, as you can see. Basically, these three things are critically important for building computers. And in each chip, you have elements of that. It happens that memory and storage chips don't have a lot of computation units inside, computation pieces inside them. But in order to build all of these, you really need to understand the logic gates and logic blocks we will discuss today. Okay, these are some pictures that go there. So this is another view of this. Basically, you have a processor that has control and data path, and you have a memory, and you have I/O. And we're going to cover all of these with most focus on processing in the first, let's say, 2/3 of the course, if you will. But we will actually talk about memory, like sequential elements as well, next week. Okay, as we said, we're going to look at an overall view. So what will we cover? Just to give you an overall view of what's coming. The first 1/3 of the course is about digital design. We'll cover combinational logic, hardware description languages, sequential logic, timing and verification. And then we will jump up to instruction set architecture, which is the software-hardware interface, and give 2 examples. We'll do some assembly programming, and you will do some of these in your labs also. And then we'll do a deep dive into microarchitecture and ISA, talk about microarchitecture and then other paradigms that change the ISA. And then in the last third of the lecture, we'll cover a lot of memory technology and organization, hierarchy, caches, multi-core caches, prefetching, virtual memory, etc. And then in the second year, you'll talk about systems programming course, which actually will talk about virtual memory also, and these concepts at a higher level of abstraction, if you will. It will not go into this much detail, but virtual memory is very common between operating systems and computer architecture, as we will see when we get to it. That's lecture 25 or so. Okay, again, you can predict what may be coming. We're going to cover a lot of processing paradigms. I've listed all of these, and all of these are actually employed in today's systems. Different systems or different systems employ a combination of these different paradigms. So you're going to learn a lot, basically. And these paradigms actually cover across the stack also, programming languages, including programming languages. Okay, but now let's go into combinational logic circuits and design. So we'll essentially start with transistors, as I promised, and then build logic gates. We're going to talk about Boolean algebra. How many people covered Boolean algebra? How many people do not know what Boolean algebra is? Okay, a small fraction. Where did you cover it? In high school again? Okay. Okay, that's good. So this will be relatively easy, but we're going to take a look at Boolean algebra from the perspective of logic design optimization. How many people covered it from that perspective? How do you optimize logic gates, for example? Okay, in high school again? Okay, that's good. Yeah, I guess high schools are progressing these days. How about other people? Who does not know how Boolean algebra can be applicable to logic gates, hardware gates? Okay, that's good. That's good. There are more hands over there. And then we're going to build combinational logic circuits. And I think this is kind of all together over here. And then we'll talk about minimizing logic circuits if time permits. Before we jump into it, basically combinational logic exists in all of these systems. These systems that we have today, and you can see they span general purpose versus special purpose spectrum. They all have combinational logic elements as well as sequential logic elements. And the main distinction is sequential logic remembers what has happened in the past. Combinational logic doesn't remember. But before we go into it, we should really talk about this general purpose versus special purpose distinction, because it will come up many, many times in the future. So general purpose systems are flexible. They can execute any program, basically. CPUs are a great example. General purpose CPUs are a great example of this. This actually, Apple M1 is unfortunately not a great example of just a CPU because hardware integration, VLSI integration has been so good that we can actually put more than a general purpose CPU inside here. There's a GPU, there's an accelerator over here. So this thing actually on the left combines the GPU as well as the special purpose ASIC as well as the CPU. But the core of it is really the CPUs over here. But basically they're very flexible. They can execute any program, easy to program and use as a result. But because they're general purpose, focusing just only on the CPU, they don't provide the best performance and efficiency because they're very general, right? They don't specialize the hardware to the program that's executing. As you go from left to right, you become more and more special purpose. So GPUs are a little bit less general purpose. They're designed for graphics and they still have remnants of the design for graphics in them, but they become much more general purpose than in the past also. It used to be that they were fixed function. GPUs in the past were more or less ASICs actually. Over time, they became more and more programmable, so they moved to the left over here over time, over the course of last 25 years or so. But they're still less general purpose than here. And then if you go to the next part, that's FPGAs, these are more reconfigurable. Because they're reconfigurable, you can configure them to adapt to the application. So they're a bit more flexible. And then on the right part here, you have ASICs, application-specific integrated circuits. These are actually designed for one application or a family of applications. In this particular case, machine learning, as we discussed. So they're much less flexible. So as you go from left to right, these become less flexible. What does that mean? That means they can either execute a limited set of programs or they're good at executing limited set of programs. Whereas here you can execute any program on the leftmost side. When you become more special purpose, you also become difficult to program and use because now you actually need to adapt to the idiosyncrasies of the hardware that are designed for a particular application. But these are extremely efficient and high performance. So energy efficiency and high performance of a well-designed ASIC is not beatable by a CPU, GPU, or even an FPGA. And there's a lot of research that shows that in terms of energy efficiency, for example, there could be 1000x difference between a CPU and an ASIC. Of course, this number depends, but 1000x is a reasonable number to think about. If you want to get 1000x improvement, that's 3 orders of magnitude improvements in terms of energy efficiency and somewhat close in performance, you should build an ASIC. But there's a trade-off. If you build an ASIC, it'll be difficult to program, right? And you will not be able to apply it. Okay, I built it for, I don't know, deep neural network model X. I want it for deep neural network model X times 100 that will happen 10 years down the road. Well, your ASIC that you build today may not be applicable for down the road 10 years later, right? So these are trade-offs. And again, this is very similar to architecture trade-offs. I'm not going to go into that, but you can think about the trade-offs. Okay, any questions? I like analogies. How many people use this thing? That's a general purpose wrench. Okay. How many people use this thing? It's a special purpose wrench. And you see a similar trade-off between them that I see? Okay. Basically, this is very similar, I think. A general purpose wrench is flexible, can work with any bolt. It's easy to use because, I mean, you can make it work with any bolt. But unfortunately, it's not the best fit to any bolt because that thing that you need to adjust never perfectly fits, if you know what I mean. If you use one of these, you would know what I mean, basically. And actually, over time, with aging, etc., it becomes loose and you basically throw it away. That happens also because it doesn't fit really. So that's basically what this last part is. On the other hand, the special purpose wrench is very efficient and gives you high performance, assuming it fits to the bolt that you're trying to tighten or loosen. But it's usually more difficult to use because of this. Well, partly because of this, because you'll need to figure out basically which one of these special purpose wrenches that you're going to use for the bolt that you're dealing with. It may take some time to figure that out. And it's inflexible. It's only for fitting bolts, basically. This is much more flexible. You could use it for other things potentially, where things may not be imaginable with these, right? So I think that's a very good distinction between a general purpose CPU on the left and a special purpose ASIC on the right. And actually, ASICs, if you really want to cover the space of many important applications, you need to build different ASICs, right? It's very similar to different special purpose wrenches. Okay, so these are some more pictures for you. So I should say that modern general purpose SoCs are not just GPUs, are not just CPUs. You can see that These are the CPUs over here. But there's also GPUs, there's also neural engines, which is accelerators, and then there are other accelerators they don't talk about over here. And they're caches, as you can see. And these are becoming bigger, as you can see. So yesterday I showed you a number, I told you a number, 24 gigabytes, but I was actually wrong. In the biggest system that Apple manufactures today, it can be 128 gigabytes of memory. This is unimaginable in the past. It was unimaginable in the past. So we're actually getting to numbers that are a bit crazy. And these are actually mobile type of systems, right? If you can build much bigger systems that are on the data center. Okay, I don't want to focus too much on the numbers, but this is where we are today. So this is another general purpose microprocessor. Again, the biggest thing here is the cores, CPU cores. But today, everybody is integrating GPUs also. Where's the GPU? I guess there's a media engine over here, as you can see. And there are different types of CPUs over here. Oh, there's the GPU. Okay. Modern GPUs are also kind of heterogeneous. They have GPUs, and they may also have some small CPU functionality in them. So heterogeneity is another principle that everybody is trying to exploit, because applications are heterogeneous. And there's no such thing as just a graphics application that today. So these are actually more general purpose systems. As systems become more general purpose, you need to integrate more components to it. If you look over here, this is from NVIDIA, I believe, and it's NVIDIA Tegra SoC actually. You can see that there's a big GPU over here. It's not the biggest GPU that NVIDIA manufactures, but there's also a CPU cluster over here. Okay, FPGAs, this is the FPGA that you're going to deal with in the labs. We're going to talk more about that next week. But modern FPGAs are actually more complicated also. This is also not the biggest FPGA. But we'll talk more about that next week. And these are the more special purpose chips. And this is another special purpose chip just for systolic array-based special purpose chip just for machine learning, as we discussed. It's a TPU. And then these are some examples that we've also seen. And then there's other special purpose ASICs for video, as you can see. And you can also see that there's heterogeneity in these chips. There are CPUs. You can actually do general purpose computation in many of these systems today, because there's usually a CPU in there, but that CPU may not be very powerful, because the goal is really to do in this particular case, to do video encoding and decoding. There's a CPU to make sure that that runs well. And you could also use it for computation, but because it's not powerful, it's not going to be able to compete with a system that's really designed to have very powerful CPUs. Okay, these all look the same. I'm going to skip the slide relatively quickly, because you're going to see this over time. You use different languages also for these things. So we're going to use Verilog, and we're going to talk about that again next week to program the FPGAs. And ASICs are actually kind of similar, but microprocessors are different. So basically, in the labs, what we will do is we're going to learn how microprocessors work. So we're going to design a microprocessor on the FPGAs. So by programming the FPGA, we're going to build a microprocessor on FPGA. So you can actually, an FPGA is so flexible that you can actually build anything on it, assuming there are enough resources, of course, hardware resources. And today's FPGAs are humongous. You have a lot of hardware resources. You can put a lot of things on there. It's still very difficult to put a very large out-of-order CPU in a single FPGA. But that's what we're going to do in the labs, actually. It's an interesting exercise. This is called prototyping. You're going to prototype a microprocessor on top of an FPGA. Now, we didn't have to do that. We could actually do some acceleration. For example, take some program and accelerate it on the FPGA, put a piece of it on the FPGA, but we're not going to do that. And we're going to use the Verilog language. Okay, so that's some roadmap. Now let's start with the building blocks of modern computers. That's the transistors. So let's see. So computers are built from simple structures, transistors. And just to give you an idea, in 1971, the first chip that was built with, at least the first prevalent chip that was built with metal oxide semiconductor transistors, which I'm going to introduce, had only 2,300 transistors. About 30 years later, Intel's Pentium 4 had 42 million. Now, about 22 years after that, which is more than 50 years after the first microprocessor, now we're at 67 billion transistors. So these transistors are the things that we're going to build logic gates on, and they're going to enable the computation. So we're going to learn how the MOS transistor works as a logic element. I'm not going to go into the device level details. You will have to take a microelectronics design course. Those are also fascinating. So we'll start with this one. How these transistors are connected to form logic gates, and how logic gates are interconnected to form larger units that are needed to construct a computer. So let's start with the transistor. So we're going to combine conductors, which is metal, insulators, which is oxide, and semiconductors, which is S over here. And we get a transistor, MOS transistor. That's why it's called a MOS transistor. It combines these three things. And again, there's a lot of fabrication technology that goes into this. I'm going to refer you to a video later on, but we cannot go into below this abstraction level in this course. And this is what a transistor looks like, an old one. And it has metal, insulator, and semiconductor in different parts of it. And your book has pictures also. So why is this useful? Basically, you can combine these to form logic gates, as we will see. And as I said, the electrical properties of these are beyond the scope of this course. I'm going to draw the abstraction level saying that I'm going to abstract this as a switch, essentially a switch that you can turn on and off. And that abstraction level is actually beautiful because if you use that abstraction level, you don't need to understand what's going on underneath as much. In some cases, you will need to, as we will see soon also. But in general, you don't need to. So again, if you want to learn about that, take a microelectronics design course. And Harris actually, sections 1.6 and 1.7 are nice in the sense that they provide lower level explanations a little bit, even though they don't go into reasoning as to why things happen. If you want to know the why, you have to take a microelectronics design course. So we actually have, in modern fabrication technologies, we have two types of MOS transistors. One is N-type, the other is P-type, NMOS or PMOS. And N-type looks like this, and P-type looks like this. And a transistor has a gate on which you apply voltage. And if based on how much voltage you apply to N-type or P-type, this acts as a switch or it acts as an open circuit, meaning source and drain gets connected or disconnected. If source and drain are connected to each other, it acts as a wire. If it acts as a wire, that means electrons or holes can flow through the wire, and there's some conductance that's happening. That means the circuit is operational. If it acts as a broken switch, meaning there's the drain and the source are not connected, then there's no transmission on the wire because it's not a wire anymore. There's something breaking it. As a result, there is no conductance. And that's the basic principle, right? That's the basic principle of a switch also. When I press that switch over here and on the light, for example, something similar happens. When I press it, right now it's actually there, it's a wire. There's a wire getting connected. If I press that switch, assuming that's connected to lights, actually it's over here probably, but I'm not going to touch that. But basically, when I press that, what happens is that wire gets broken. As a result, electricity doesn't flow. And as a result, we don't get conductance and we don't get lights. But these are two fundamental types of transistors, and they operate differently, as we will see. And they both operate logically, as I just said. So let me actually demonstrate that. This is the wall switch. There's a power supply and there's a light bulb, simplified. In order for the lamp to glow, electrons must flow. And in order for electrons to flow, there must be a closed circuit between the power supply and the lamp and back to the power supply so that electrons keep flowing and power supply keeps generating electrons, essentially. Okay, and the lamp can be turned on and off by simply manipulating the wall switch. So this wall switch can break or make the circuit. If I press it again, it becomes an open circuit. If I press it again, it becomes a closed circuit. And I could keep doing this forever in my life, right? Okay, even cats can do it. So they're actually very smart. Okay, but instead of the wall switch, we can use a transistor, N-type or P-type, to make or break the closed circuit. So this is what a transistor looks like. In this case, it's an N-type. We'll see why it's an N-type transistor. But an N-type transistor, when you supply high voltage to the gate, the connection from source and drain acts like a piece of wire, meaning the circuit gets closed. So it can conduct. It can conduct electrons, basically. So depending on the technology, this high voltage can range from 0.3 to 3 volts. You don't need to know about that, but there's some threshold for the voltage. And this is called a threshold voltage, actually, that enables a transistor to operate operate the way we would like it to operate. And if the gate of the N-type transistor is applied a 0 voltage, the connection between the source and drain is broken, meaning this becomes a open circuit. So there's no conductance that happens. Let's take a look at it now. We will replace the switch over there with an N-type transistor in the same circuit with a battery and bulb. Now, if we apply 0 volts over here, the circuit is broken, meaning open. So there is no conductance. As a result, the light doesn't glow, right? Now we apply 3 volts here, high voltage. there should be some threshold voltage that you go higher, and there's a lot of noise over here. These are fundamental operations of this. These are all analog, but for the analog operation, you need to take the microelectronics design course. I'm going to build a digital abstraction from that analog. If you apply 0 volts, this is open. If you apply 3 volts, now this piece, this transistor acts as a wire, and as a result, light glows. Now you can ask me, what if I apply 2.4 volts? Well, it depends on the analog characteristics of the device, right? Usually there's some noise margin, meaning between 0 to, I don't know, 1.5 volts, you usually get a closed, an open circuit. And between 1.5 to 3 volts, you usually get a closed circuit. So there's some margin that you need to obey. If you're too close to 1.5, you may get some random value, basically. That's where the analog comes in. That's why you need to make sure that your voltages are good. And today voltages are reducing, so these margins are also reducing. That's part of the reliability issues that we're going to see. Okay, but the basics are hopefully clear, right? And we represent it this way also. This is an N-type transistor. You'll see it almost always at the bottom, and we'll see why also. This is short-hand rotation. There's this is the power supply over here, high voltage, and this is ground, low voltage, and light bulb is connected over here. If the gate is turned on, meaning high voltage is applied to the gate, this acts like a wire, such that electrons flow from high voltage to the low voltage, right? Hopefully that makes sense. Now, this was N-type. P-type transistor works in exactly the opposite fashion from the N-type transistor. Basically, if you apply high voltage to the gate, it gets turned on, meaning the source and drain gets connected, so you get a wire. If you apply low voltage to the gate, it gets turned off. Did I say that right? No, it should be the opposite, basically. I just described N-type transistor again. If you apply high voltage, it gets turned off. If you apply low voltage, it gets turned on. And we distinguish that with a bubble. Okay, so this is the N-type transistor. The circuit is closed when you apply high voltage. This is the P-type transistor. We have a bubble, which means that you need to invert things. So if you apply 0 volts, it gets inverted and it acts like a inverter, and you get, it's as if you apply a high voltage to the N-type transistor. So that inversion is basically showing that this works exactly the opposite way to the N-type transistor. And why do we have different two types? We're going to briefly talk about that later on, but these are all based on fabrication technologies. The principles with which N-type transistor operates. In N-type transistors, actually, you take advantage of electron flow, whereas in P-type transistor, you take advantage of the hole flow. So holes versus electrons are different components. And in the past, actually, people did not figure out how to make the holes flow very well. As a result, past computers were built using NMOS. But now we're very good at building PMOS transistors as well. As a result, we actually are much better. And we'll see how we will connect these. Does this make sense? So transistor is now a switch for you. You don't need to know anything else below this abstraction unless you start asking questions about why can I not connect these transistors this way or that way? Then you need to know the analog properties. But if you want to have a good basis of transistors and build logic gates, you don't need to know underneath if you actually already built some good logic gates with them. Okay, so now let's build some logic gates. This is one level higher in the abstraction. Now we know how this transistor works, at least good enough to our abstraction level. We're going to go a little bit more. How do we build logic structures out of most transistors? Okay, these logical units that we build out of most transistors are called logic gates. And they implement simple Boolean functions. We're going to start with an inverter function soon. And I mean, you've all taken Boolean, well, most of you know about Boolean algebra. Probably most of you did not read George Boole's seminal book, but it's beautiful. Basically, we're going to use the CMOS technology, complementary metal oxide semiconductor technology. The reason we're going to use it is because it's a dominant technology today. This doesn't mean that it's going to be dominant 20 years down the road, but it's been dominant for a long period of time. In the past, as I said, we used just NMOS technology, which was not as good as CMOS. So NMOS plus PMOS is actually CMOS in the end. You have both types of transistors, basically. And basically, let's take a look at the simplest logic structure that exists in a modern computer. It looks like this. Maybe I'll ask you, what does this do? I kind of already gave you a side channel in the earlier slides. Anybody? So what did we do over here? Basically, we have a PMOS transistor up here at the top, it's connected to high voltage, 3 volts. This is also called a power rail. And then it's the bottom of the transistor is connected to the output, and the gate is connected to the input, which we call A. And then we also connect the input to an NMOS transistor at the bottom, which at the bottom is connected to 0 volts, and one end of the transistor is connected to the output. And you supply input to both the PMOS transistor and the NMOS transistor. And based on the input you supply, 0 volts or 3 volts, we want to guess what the output is. So based on what I just told you in the prior slides, you should be able to guess what that output is if that input is 0 volts. So if that input is 0 volts, what do you expect the output would be? 3 volts. Okay. So if that input is 3 volts, what do you expect the output to be? Okay, maybe I'll take it. 0 volts. So basically, it inverts the input, right? It's called an inverter because it basically gives you the opposite voltage. Okay, let's take a look at why that's the case. Well, I already described this P-type, N-type. Okay, so you already answered these, some of you at least. If you didn't get it, let's now go through it. Basically, if you apply 0 volts over here, we said that, let's start with the NMOS at the bottom. The NMOS doesn't get turned on because it gets turned on, meaning it becomes a closed circuit only if you apply 3 volts, but we're applying 0 volts. So this is an open circuit. So the output gets disconnected from 0 volts. The PMOS transistor, on the other hand, becomes a closed circuit if you apply 0 volts to it. Remember the inverter over here? You can think of it actually like this. I like thinking of it this way. When you get 0 volts, this little bubble inverts it to 3 volts. And then you can think of this as an NMOS transistor at that point. It doesn't exactly work that way also, but logically you can think of it that way. But as a PMOS transistor, if you apply 0 volts to the gate, it becomes a closed circuit, meaning 3 volts gets connected to the output. Now, if you look at this, 3 volts gets connected to the output, 0 volts doesn't get connected. So the output and input based on circuit structure should be the same. And output, basically electrons flow from 3 volts to whatever the output is, and output becomes 3 volts. Does that make sense? Okay. So you can also think of this as P-type transistor pulls the output up. And it turns out P-type transistors are good at pulling the output up. Okay. And I like this also. P means up, N means down. And this is going to be the reason why we cannot put P-type transistors to the bottom. We cannot connect that to 0 volts. And we cannot connect N-type transistors to the top 3 volts because they're not good at pulling up. This is a fabrication. Unfortunately, this is the property of the analog device. Okay, so let's take a look at what happens when the input is connected to 3 volts. Okay, I'm going to show you. Basically, exactly the opposite thing happens. Input is 3 volts. The gate of the NMOS transistor gets 3 volts. As a result, NMOS transistor acts like a closed circuit. And the output over here gets connected to 0 volts. And the PMOS transistor acts as an open circuit because if it gets 3 volts based on what we described, it acts as an open circuit. So the 3 volts, the power doesn't get connected to the output. Output basically gets pulled down to 0 volts. And N-type transistor pulls the output down. And remember this again, N is good for down. Okay. And this is your CMOS NOT gate. This is basically the first logic gate to be built. It only requires 2 transistors, as you can see. Why do we call it NOTs? I think I already explained this. It inverts the, digitally, it inverts the output, basically. It inverts the input. So one possible interpretation is you can interpret the 0 volts as a logical or binary value of 0 and interpret 3 volts as logical binary value of 1. So you can encode these voltages. 0 volts mean 0 and 3 volts means 1 logically. You can also think of this as false and true, right? 0 is false, 1 is true. You don't have to do it this way. This is just an encoding, right? You could have encoded the other way around also. But let's keep it like 0 is 0, 0 volts is 0 logically, and 3 volts is 1 logically. So you can build a truth table out of this. So this is a truth table. A truth table lists for all possible combinations of inputs, what should be the output, or what is the output of the circuit. And these are the intermediate things that happen to the P and N transistors over here. So if the input is 0, logically, P transistor is on, N transistor off, as we discussed, and Y becomes 1, because P transistor pulls up the output. If the input A is 1, P transistor is off, N transistor is on, and the output Y becomes 0 because the N transistor pulls down the output. So this is your first basic truth table. And this is logically Y equals A bar, a complement or complement of A. Okay. And as a logic gate, we represent an inverter like this. Again, inverter, this bubble is always an inversion sign. Without this bubble, this will be a buffer, as we'll see. So it will not, if you have this bubble, Y equals A bar. If you don't have this bubble, Y is equal to A. So if you just have the triangle, Y is equal to A. It's a buffer to amplify the signal, as we will see later on. Okay, bubble indicates inversion. So we already discussed the truth table. This is actually the simplified, this is a real truth table that corresponds to logical output of the circuit for each possible input. In this case, we have a 1 input, 1 output circuit. This is the simplest thing that we have. Okay, let's build a little bit more complex gates. We still have some time. So what is this? This is a more difficult question for you. Now we have two P-type transistors on top connected to the output. And we have two N-type transistors, they're connected to the output in parallel, and two N-type transistors connected to the output in series. And as we said, N-types are good at pulling down, so they're at the bottom. P-types are good at pulling up, so they're at the top. And the input A is connected to P1 and N1, and input B is connected to P2 and N2. So what does the circuit do? Tougher one. Not a simple inversion anymore. Anybody? I'm not going to wait too long because if I wait too long, yes, please. It's an AND gate, you said? Both inputs are 3 volts. Unfortunately, no. That's a good try. Yeah, you need to run through it. Let's run through it basically. So let's take a look. Let's build a truth table. It's more complicated. Now, if A and B are both 0, so basically, if you think about it, P1 and P2 are in parallel. Only one of them must be on to pull up the output to 3 volts, right? So if A and B are both 0, both P1 and P2 are on, right? And N1 and N2 are off, actually, because of the way we designed the circuit. And the output is equal to 1, because P transistors, if any of these are on and all of these are off, well, any of these are off. If any of these are on and any of these are off, you pull up the circuit, right, to the 3 volts. Okay. If you look at the other input combination, A is 0, B is 1. One P transistor is turned on, so output gets connected to 3 volts. But one N transistor is turned off, so output doesn't get connected to 0 volts. So we still get 1 at the end because the circuit is pulled up and there's no connection to 0 volts. And as you can see over here, that animation came earlier, let's say. If you look at it over here, again, if A is 1, B is 0, the P2 gets connected to, P2 becomes a closed circuit, so output gets connected to 3 volts, but one of these transistors is still off. As a result, output doesn't get connected to 0 volts. So you still get 1 at the end. So for both P1 and P2 to be off, both of the inputs should be 1, meaning high voltage. At that point, both of these are off. The output doesn't get connected to 3 volts, but both of these are on at this point. As a result, the output gets connected to 0 volts. So now what we have is for the circuit, for the output to be 0, both A and B should be 1. Does that make sense? So it's a little bit more sophisticated than an AND. It's really ANDing A and B and taking an inversion of it, right? It's the inversion of A and B. And basically, the key takeaway is P1 and P2 are in parallel. Only one must be on to pull up the output to 3 volts, and N1 and N2 are connected in series. Both must be on to pull down the output to 0 volts. So we call this the NOT of A and B, or NAND, if you will. And this is how we show it. So this is and there's a NOT at the end. And this is the truth table, basically, which is the same truth table as I showed you earlier. Y is 0 only if A and B are 1. So AND gate, and I'll give you the AND gate and then we'll finish. How do we make an AND gate? Basically, this is the AND function, if you will, A and B. Basically, you take the NAND and invert its output. That sounds good, right? Unfortunately, this is the only way we can build an AND gate reliably in CMOS. You can come up with some other way. You have to put the N-type transistors and connect them to 3 volts, but that would violate what I said. N-type transistors are not good at passing electrons. They're not good at pulling up the output. This is where the analog operational characteristics matter. You cannot just treat the transistor as a switch at this point, because you need to know that the NMOS transistor is bad at pulling up the output. And if you cannot place it to the top, and if you cannot place the P to the bottom, this is really the only way to build an AND gate. So this is why CMOS is called inverting logic, because of the properties of the transistors. You get the immersion easily, but you don't get the, let's say, the regular value, non-complemented value easily. You have to invert it. You have to invert the inverted value. And that's what we did over here. You have an AND gate, and if you want to get the AND, you invert the result of the AND gate over here. And you can convince that this works. But any other trick that you play, you have to put the NMOS transistors to the bottom. That's, I guess I kind of have this food for thought. Can we not use fewer transistors for the AND gates? Unfortunately, based on what I said, no. You need to use 6 transistors. Whereas you could come up with a structure where you can use 4 transistors, but I will guarantee you that it doesn't work in the properties that we have for PMOS and NMOS transistors analog. Okay, so I'm going to stop here, but this is what we've covered today. These are the NOT, NAND, and AND gates. Next week, we're going to talk about the general CMOS gate structure, and we're going to cover a lot more in combinational logic. Okay, have a great weekend. I'll see you next week.